welcome back. So, today we shall be studying on our next topic, which is essentially a background on cryptography and also to have an understanding of what is meant by cryptanalysis. So, and finally, we shall be talking about the Advanced Encryption Standard or AES. So, to start with our concepts that or the concept that we shall be covering in today's class, we shall be trying to understand the goals of cryptography, try to understand the various types of cryptographic algorithms. I would say like broad classifications of cryptographic algorithms. In particular, we shall be trying to look into block ciphers, which is a very common form of cryptographic algorithm which is used to encrypt bulk volumes of information or data. And we shall be looking into one particular encryption or block cipher, which is called as the AES or Advanced Encryption Standard, which is the de facto worldwide standard for block ciphers. So, to begin with, let us try to look into the goals of cryptography. So the goals of cryptography are typically depicted by this three-party scenario, where you have got two legitimate players, Bob and Alice, who are essentially trying to share some information over an untrusted channel. So, this untrusted channel is essentially also observed by an attacker or an adversary, which is typically denoted as Eve. So, Eve is interested to know what is the communication which is essentially being done between Bob and Alice. So, in order to prohibit Eve from getting access to this information, Bob tries to resort to cryptography. Bob tries to apply cryptography and tries to apply the data or tries to apply it on the data and communicate this information to Alice. So, there can be different goals of cryptography. Confidentiality is one of the most important goals, as I said, because Eve will be probably curious to know what is the information being exchanged, and in that context Bob often encrypts this information and sends it to Alice. So, once it is encrypted, the idea is that it looks like a jumbled piece of data from which Eve is not able to understand or make any inference about the actual content of the message. So, so now I would like to mention here that although we often kind of synonymously use cryptography with confidentiality, but that is not the sole goal of encryption or cryptography. Okay, that is not the sole goal of cryptography. So, there may be other important goals. For example, I may be only bothered about integrity of information. So, I may be only bothered to ensure that I am not really bothered to ensure that Eve does not have access to information, but rather I may be bothered to ensure that Eve is not able to corrupt that information or is not able to modify that information. Okay. So, therefore, while confidentiality is often ensured by encryption, for integrity there may be other primitives which are used. So, it could be typically a hash function or a message authentication code which could be deployed to achieve integrity. But at the end of the day, with several goals, like you may have confidentiality as your goal, integrity as your goal, and you may try to apply cryptographic algorithms, but all cryptographic algorithms comes with overhead, comes with essentially making the process slow, kind of making the process cumbersome. So, therefore, we should ensure at the end of the day that data should be available. So, we should ensure the data should be available to the legitimate persons like Bob and Alice, and Eve should not be able to subvert availability of information. Okay. So, there should be suitable mechanisms which also allows you to have I would say uninterrupted access to information or uninterrupted access to data. So, therefore, let us try to take a one by one look into these various objectives. So, the first objective, as I said, is confidentiality. So, information is exchanged over the untrusted network. So, information while exchanged should remain secret. That means, when you are exchanging information over the untrusted network, you should ensure that it should remain secret to the legitimate players, to the sender and to the receiver. That means Alice and Bob in our context. So, confidentiality is related to both, not only with respect to transmission of information, but also it could be with respect to data at rest. That means it should be related to also data which is kept in your storages. So, it could be in your disks, it could be in your drives and other storage media. Okay. So, likewise, as I said that integrity is also an important objective. So, as we know that information, one of the important criteria of information is that it is always changing, and that is probably even more relevant with today's discussions on big data and so on, where information is continuously being generated and is an expansive database, So, but the charge, so therefore, right, we should ensure that the responsibility of the persons who are essentially providing service should be that unauthorized people should not be able to modify that information. So, that means like for example, if I have got some amount of data which is for example measuring the amount of money that I have in my bank, an unauthorized person should not be able to modify that data, okay, because you can easily understand that if that data is modified, then that can lead to catastrophic consequences, okay. So, therefore, we need to techniques to ensure that there is integrity of data, which means like somebody should be who is not licensed or is not legitimate should not be able to modify that data. And moreover, right, if there is any modification which is being done, I should be able to readily understand that there has been a modification being done. That means it should be detected. Any modification should be easily detected and should be essentially lead to follow up measures to ensure that there is really integrity of information, okay. So, likewise, confidentiality and integrity should not hinder the availability of data. That means, right, I may apply cumbersome techniques, but at the same time, right, we should ensure that availability is a very important goal, right. I want to make things efficient. So, therefore, right, data must be available to authorized users at any time, okay, and therefore, right, we should also always keep in mind cryptographic mechanisms which we are adopting should essentially be implemented in a manner that they essentially incur less overhead. In terms of various performance footprints, it should have less a less footprint, okay, and that essentially makes hardware design so important, because when you have hardware design for cryptographic algorithms, you essentially have an opportunity of making them optimized, okay. But at the same time, right, we also need to tackle other criteria, like for example various kind of threats which can also be targeted specifically for hardware, okay. But in terms of performance, right, hardware provides immense opportunity of realizing lesser footprints on various criteria, okay. So, for example, right, you can, as I said probably in one of my introductory classes, that if you go for hardware design of complex cryptographic algorithms, there is an ordered improvement over your software designs, okay, and therefore we need to probably study about how we can make efficient hardware implementations of cryptographic algorithms. So, therefore, right, you can definitely have different mechanisms like cryptography of cryptographic algorithms. You can have encryption, you can have hash functions, you can have signature schemes, you can have you can apply public key cryptography for signatures. So, there are like lot of cryptographic algorithms which have been developed, but we need to understand about where to apply what, okay, and that is typically what we study in a cryptography course. So, therefore, one of the I would say salient features of all these cryptographic algorithms is that the algorithms are published. That means the algorithms that we deploy for encryption or for signatures, they are all published. That means they are available to even our adversaries. What is not available to an adversary is the piece of secret which is called often as the key, okay, and therefore, right, the objective of the attacker is to obtain this key from the communication, and the objective of the defender or the designer is to ensure that the information that is exchanged, it could be the ciphertext, it could be the plain text, it could be the ciphertext plain text combinations, that should not reveal information about the secret key, okay, and therefore, what we, right, as designers want to protect is the secret key. So, therefore, right, if you try to understand in a more formal setting what is a cryptosystem. So, essentially cryptosystem is a 5 tuple often denoted by this like P, C, K, E and D, where P stands for the set of possible or finite set of possible plain texts, C stands for the finite set of possible ciphertexts, K is the key space, okay, it is a finite set of possible keys from which I choose a specific key. Now, the moment I choose a specific key, for example, a small k for example, then two things gets decided. One is what is called as an encryption rule, and the other one is what is called as the decryption rule. So, the encryption rule, which is denoted as say EK, belongs to this encryption family, and likewise DK belongs to this decryption family. So, there is a very important criteria which you can easily probably understand, is that the process should be reversible, right. That means when I encrypt a piece of information and when I decrypt it, I should get back the original data, and that is being denoted here in a more formal way, which says that for each EK, that means which is essentially a mapping from the plain text space to the ciphertext space, and for each decay, which is essentially the reverse mapping from ciphertext to the plain text space. So, these are functions such that for all x, which is essentially belonging to the plain text, when I apply the encryption function on x and I get ek of x, and then I apply dk of x, which is the decryption function, I should get back x. So, therefore, this process should be reversible. So, this invertibility is a feature which all encryption, whether it is like symmetric key or public key, as we will soon study, all of them should satisfy this property. Okay. This is a salient feature because we want to decrypt back the original data. So, therefore, there are two different broad classes of cryptography which people have studied. The first one is probably very intuitive, which is called as symmetric key cryptography, which means essentially it means those encryption algorithms where the encryption key and the decryption key are same. That means, if I want to encrypt a piece of information and if I want to decrypt the cipher, then I essentially share that key with my recipient. Okay. So, there has to be some kind of trusted channel through which that secret key has been shared. Now, you can immediately understand that if there are n players in a network and if all of them are connected with each other, then the number of keys can increase exorbitantly, can increase quadratically, and therefore, we need to have efficient mechanisms to do this key exchange. And therefore, there is another class of cryptographic algorithms which are called as asymmetric key cryptography, which essentially gives a very nice solution for this particular problem. So, therefore, in this setting of asymmetric cryptography, there are two keys, one which is called as a public key, the other one which is called as a private key or the decryption key. The idea is that the first important thing to note is that the encryption key and the decryption key, or the public key and the private key, are not the same. Okay. So, what we often do is that with public key we can encrypt. That means, suppose Alice wants to send a piece of information to Bob. So, therefore, what Alice does is that Alice encrypts it. Okay, and it encrypts it with Bob's public key, and now Bob, since Bob only has his private key, can only decrypt that message. That means, anybody can encrypt that message and send it to Alice, but send it to Bob, but only Bob can decrypt it because it is Bob's own private key. Okay. So, therefore, that essentially is nice because in that case the key exchange problem is nicely handled in that case. And the assumption behind these class of problems is often based upon a candidate hard problem. That means, a problem which is believed to be hard. The idea is that it is believed to be hard to derive the private key from the public key. Note that Alice's public key is known to everyone, but what is important is to ensure that it should be difficult for Eve, who is an attacker, to infer the corresponding private key of Alice from the public data. Okay, and the way these kind of reasonings are done is often based upon a hard problem. So, the hard problem could be, for example, factorization or some other hard problem which is believed to be hard, which is believed to be computationally intensive. So, therefore, let us first of all try to look into the one very important class of symmetric key encryption, which is called as block cipher, and block ciphers are typically used for bulk data encryption. So, therefore, in block cipher, what essentially is done is that, as the name suggests, it basically encrypts n bits of plain text, which is called as a block. So, what essentially is done here is that you take the plain text and you divide it into chunks of data, all of them are like blocks of information, and then you start applying your block cipher. So, the block cipher takes one block of data, takes the secret key, and then obtains another block of ciphertext. This process could be either repeated block by block, or there could be some modes where you do chaining, for example. Okay. But the whole idea is that when you are having this kind of encryption algorithm, then this encryption algorithm applies on one block of data. Say, for example, it could be 128 bits of data, as we will see in the case of AES 128, and produces ciphertext which is also 128 bits of data. Now, the key is often also of a similar dimension. So, it could be like say 128 bits or say 256 bits on which you are applying your encryption process. So, therefore, the block cipher takes two inputs. Okay, it takes the plain text and the key and produces a ciphertext. So, basically it is a mapping from the plain text and the key to a ciphertext space. Okay. So, therefore, that is denoted here as this function, which is C is equal to EKP, which means like it is an encryption function which is kind of parameterized by the key, and it operates on a plain text P and produces a ciphertext C. Okay. So, now you can, if you want to decrypt it, as you can easily understand, then you need to have an invertible process. So, you need to have a reversible process, right. So, therefore, what the decryption function does, it applies on a ciphertext again on a block of data, again applies the same secret key. Remember, it is a symmetric key algorithm. So, it has got the same secret key on which this also works, and therefore, right finally produces that the starting block of the plain text, okay, and that way the plain text is recovered block by block. Again, you can, if you are depending upon the mode in which you are applying the encryption, you have to apply a suitable mode for decryption. Okay. So, therefore, the block cipher decryption algorithm is denoted by this function, where I take the C, which is my cipher text, and again I take my function which is denoted as dk, and I obtain back the plain text. Okay. So, now so therefore, right, if I want to now zoom into the block cipher, for example, then this is how the internal of a block cipher typically looks like. So, these block ciphers are what are often called as product ciphers or iterative ciphers. So, what it does here is that it takes a plain text block, it takes a secret key, and the first step is usually a key whitening step. So, this key whitening is usually applied or obtained by some kind of reversible key mixing process. A very common form of reversible key mixing is by applying a bitwise exclusive OR. So, therefore, I take this plain text, I take the secret key, and I do an XOR between the plain text and the key and obtain the input to the first round. And then I have a period, like a very regular structure of applying the rounds. That means, rounds essentially are constituted by some kind of operations. These operations are applied one by one in an iterative manner. So, for example, in this case I have shown that there are n rounds. This number of rounds is often fixed by something which is called as cryptanalysis, which is essentially an evaluation methodology of the cipher against various known attacks. And then once you know that, okay, n rounds are required by the cipher, then for every round you also need to have something which is called as a round key. So, this round key is derived by an algorithm which is called as the key expansion algorithm, or also called as the key scheduling algorithm. So, this key scheduling algorithm takes the secret key and derives the round keys one by one. So, here you can see that from the secret key we have got the round key 1, round key 2, and so on till round key n, and all of these round keys are mixed with these rounds. Okay. So, this mixing is also done by a similar step as the key whitening step. For example, it could be done through a bitwise exclusive OR. Okay. So, you can also apply other kind of whitening things, whitening steps. For example, you can probably try with an integer modular addition also. So, there could be other kind of reversible functions which you can also try to apply over here. But the most common is probably exclusive OR, where you do an XOR between the plain text and the secret key or the key components. So, finally, after n rounds you obtain an output which is called as a cipher. Okay. Now, you should note here at this point that what the designer wants you to essentially see is that it wants that the adversary should only see this plain text and the cipher text block. It wants that the adversary should not see any intermediate data. If the adversary is able to see any intermediate data, then the designer cannot give any guarantees of security. Okay. And what we will see later on in side channel attacks, which we try to do in various hardware designs, various hardware designs, is that through side channels we try to get information about these internal rounds. Okay. And therefore, we try to retrieve the key in a very efficient manner. Okay. But in a very black box sense, what I want to show here is that the attacker should only see the plain text and the cipher text, and then the mathematics or the algorithm guarantees that there should not be any efficient attack better than the brute force search. That means, for example, if the key is of dimension 128 bit, then a brute force search would be a 2 to the power of 128 guess. That means a guess with a complexity of 2 to the power of 128. So, what I want as a designer is that there should be no attack which is better than this brute force search. So, therefore, right, typically the key length and the block lengths are preferred as 128 bits, 192 or 256. The key and the block length can be independent of each other. So, therefore, you can have, for example, a cipher where there is 128 bit blocks, and the key right can be independently chosen from the block length, that you can essentially make it either 128 or 192 or 256. Okay. You can also change the block length to say 192, and again you can make independent choices of the key length. So, therefore, right, the key length and the block length could be independently chosen of each other, and the choice of the length often depends upon how effective the cipher is against brute force search. Okay. So, therefore, typically it is assumed that we should have at least 80 bits of security to ensure that we have got like enough amount of protection against computationally bounded adversaries. And the longer length should like we can of course keep longer length, but you should also again keep in mind that if you have longer length, then that will incur into more performance overhead. So, it will take more time, it will be like if you are talking about hardware design, it will consume more power, it will have more area requirement or resource requirement. So, we should try to provide good amount of security with minimum resource. That is always an objective of both algorithm designers or both cipher designers as well as people who are implementing them, who wants to make efficient implementations out of ciphers. So, therefore, if you just want to also look into what are the important criteria inside an encryption round. So, again, as we have seen that in block cipher is made of rounds, but if you go into a round, you will typically see that that there are two important blocks in a round. So, one of them essentially tries to hide the relationship between the cipher text and the key, and that is called as confusion. And the other one is what tries to hide the relationship between the cipher text and the plain text, and that is what is called as diffusion. So, therefore, you will see that in a block cipher round, typically there are constructions which provides both confusion and diffusion. Okay. So, typically the artifact or the block which produces or provides confusion is called as S box or substitution box. Okay. So, we will see in more details as we study AES and other ciphers, and the other layer which is called as diffusion is typically provided by permutations, by linear permutations or linear mappings. And then, as I said, the third important block the third important component of the round is where you are mixing the round key with your state. Okay, and that is typically done by a round key process, which is often realized by exclusivors. So, the number of rounds is determined by the ciphers resistant to known attacks, and that is called as cryptanalysis. Okay. So, therefore, talking about cryptographic attacks. So, what essentially is so therefore, the overall subject is what is called as cryptology. Okay, and there are two important components. One is where you talk about cryptography, where you design things, and the other one is what is called as cryptanalysis, where you try to analyze your ciphers or you try to attack your ciphers, but with the objective of analyzing them. So, what we try to do in cryptanalytic attacks is we try to apply mathematical techniques to obtain the key better than a brute force search, because a brute force search would mean that suppose there is an n bit key, then that would imply a 2 to the power of n guess, and we try to ensure that our construction should not be able to be attacked by an adversary who has access to plain text, cipher text, plain text, cipher text combination, should not, whether when it is knowing the plain text or whether it is able to choose the plain text, should not be able to do an attack which is better than a brute force search or brute force attack. So, therefore, we will see that most of the attacks that we essentially see are basically based on something which is called as a distinguisher. Because a good cipher essentially tries to randomize things. Okay, for example, it tries to transform the plain text distribution to appear as random in the cipher. So, the goal of an attack in general is to find out properties in the cipher which does not exist in a random distribution. So, you may probably appreciate by this fact that suppose you have got a plain text size of say 128 bits and a key size of 128 bits. It is not possible for someone to evaluate all the possible mappings, because the mapping is huge. So, therefore, the attacker always tries to see or tries to kind of explore whether there is some property which the cipher still has, which makes it distinctly different from a random distribution. Okay, and that is really a challenging objective from the designer's perspective, because the designer cannot simply see all the possible configurations, because the space is huge. So, therefore, what the attacker tries to do is that in efficient attacks, it tries to do something which is like a divide and conquer attack. So, what it tries to do is that it tries to guess a portion of the key and then it checks for the property. So, any attack which is better than a brute force search will qualify as an attack. So, therefore, if the attacker is able to find out a property which essentially is distinctly different from a random distribution, then that means that key essentially or that portion of the key gets explored. And if you can do it in a divide and conquer manner, then you essentially have an efficient key retrieval process, which is better than a brute force search. So, the objective of the designer is to ensure that our designs are not amenable to such a better than brute force search attack, and therefore, they are resistant against such attacks. Okay. And may not be, often these attacks may not be practical. That means, suppose there is, rather than 2 to the power of 128, if I do an attack with say complexity of 2 to the power of 120, it is not a practical attack, but it definitely exposes a design flaw which we would like to prevent. Okay. So, therefore, one very important message is that there is a principle which is called as Karskov's principle, which says that like the cryptographic algorithm is always assumed to be known to the adversary, and this is something that we have understood historically, that we may try to develop proprietary algorithms, but there are often like various ways through which the proprietary algorithm eventually comes to the public. Okay. So, therefore, people can either reverse engineer or even they can compromise a person who has knowledge about the algorithm. So, rather a better approach is that we will try to rely on something which is called as a key. Okay. We will try to rely upon the fact that there is a piece of information which is called as the key, and the attacker does not know the key, and therefore, the security should be reliant on the key, and therefore, even if you get hold about the encryption algorithm, then the security is not compromised. Moreover, it also tries to tell that you essentially the moment you open up your algorithm to public scrutiny, then your algorithm gets better analyzed, right, and therefore, you really come to know about some kind of flaws which may be which may have been overlooked by the designer. Okay. So, therefore, right, I mean there are different ways in which you can do cryptanalysis. So, I will try to give you a basic notion about an attack strategy which is called as differential analysis. Okay. So, therefore, right, when you talk about differential analysis, then the usual, so as I said that suppose you consider a cipher which is made of C equal to M XOR K, okay, where M is the message and K is the key. Okay. So, therefore, right, each variable you can assume to be B bit of information. So, if the key is chosen at random and used only once, then the cryptanalyst gets no information about M from C. Okay. What happens, right, if the key is used twice? So, you will see that so this is something which is often called as a one time pad, but rather what we do in practice, right, we try to use the same key for different encryptions. So, imagine that the same key is used for two encryptions, that means for encrypting M0 and as well as for encrypting M1. So, therefore, right, if I take the cipher C0 and C1 and if I XOR them, then I know that this K and this K gets cancelled because K XOR K will get cancelled, and so therefore, I will have M0 XORed with M1. So, this immediately shows that the notion of difference actually does not depend upon the key and the key gets cancelled. So, this notion of difference is actually technically called as differential, okay, and therefore, we try to calculate the differential of two states, okay, which essentially does not depend upon the secret key. So, let us do a very simple exercise on cryptanalysis. So, suppose I have got a message M, I have got this K0 key, and I obtain some intermediate data which is called as U and pass it through an S box. So, the S box is a small S box which I have shown here in the table. So, that just stands for a mapping. That means, if I have got 0 as input, then this gets mapped into 6. If 1 is an input, it gets mapped into 4 and so on. So, you can imagine that this is just as a lookup table. So, this S box or S function does that lookup and transforms U into V, and finally, I apply K1 to XOR with K1 and I get C. Okay. So, you can see that if I study the differential behavior, then we can do an interesting attack rather than like guessing all the possible values of K0 and K1. Okay. So, what essentially you can do here, so you can observe that K0 is a 4 bit of information, K1 is also a 4 bit of information. So, a brute force search would therefore require 2 to the power of 4 into 2 to the power of 4, that means 2 to the power of 8 possible guesses. So, we can do better than that, okay, and as I will show here in these slides. So, suppose you consider encryptions with a pair of plaintext M0 and M1. So, therefore, as I said in the previous slide, if you know M0 and M1, you also know U0 XOR U1, because the K will have no effect on the differential. So, once you observe U0 XOR U1, you also see that U0 XOR U1 is nothing but S inverse V0 XORed with S inverse of V1. Okay. So, you see that if I just go back here, then this XOR, the differential here can be obtained by XORing S inverse of V0 with S inverse of V1. Okay. And so, therefore, so now what the attacker will do is that the attacker will guess K1, okay, and will estimate V0 and V1 and evaluate the above. Okay. If more than one value of K1 will satisfy, then it will try with other messages. So, the observation is that the difference between internal variables will get exposed because of the difference, and this will help us to recover key information by guessing parts of the key and testing whether the differential holds. So, note that when you are guessing here, you are just guessing for K1, it is independent of the guess of K0. So, you are doing an analysis which does not depend upon K0, and you can only concentrate on one part of the key. So, you can do a divide and conquer analysis. Okay. So, here is the the actual differential attack. So, here you can see what we have done here is that you have got A, which is one of the message, and you have got K0, you have got U0, And so what and in the other pair we choose 5 as the message. Okay. So if you XOR between A and 5, then you get F. Okay. And therefore U0 XORed with U1 is also equal to F. Okay. So U0 XORed with U1 is equal to A XORed with 5, and that is equal to F. So now if you obtain the reverse S box, which you can also write, right, because it's a bijective map, so you can, rather than expressing V0 in terms of U0, you can also express U0 in terms of V0. Okay. And therefore this is the corresponding mapping which you can analyze, okay, which you can test for its validity given the previous S box. And now you can observe that for each value t of K1, we want to ensure that RT XORed with 9. Okay. So here you can see that 9 is the cipher. So 9 XORed with K1, and if I apply the R function, I come to this point U0. So I XOR RT XORed with 9, and here I XOR RT XORed with 6, where T is the candidate for K1. So I XOR T with 6, and then I apply the inverse function, which is R, and then if I XOR, then I should get U0 XORed with U1, which is F. Okay. So here you will observe that if I see the inverse function, then there are two t values shown as 7 and 8, for which I get these two f's. Okay. And therefore 7 and 8 are my candidate keys for K1. Okay. So then I repeat this process for another such pair. So here, for example, I have got it for 9 and 8, and I again repeat this process. Okay. So now I have got two key values for K1, which is shown as 0 and 7. So now if I take an intersection in between previous one like 7 and 8 and between 0 and 7, then I know that 7 is my candidate for K1, and then I can calculate K0 easily. Okay. So you see that the brute force search here is now was 2 power of 8, but I am doing this attack with a complexity of 2 power of 4, and that is definitely better than a brute force search. Okay. So therefore this is an attack. So talking about, like what we will be talking subsequently is that we will be talking about a full-fledged cipher, which is called as AES, which is also called as the advanced encryption standard. So this is a de facto worldwide standard from 2000, and there are different versions of this algorithm. So there are AES 128, AES 192, and AES 256. So the idea is that all of them have got 128 bit of plain text, but they have got different sizes of the key. So for example, AES 128 has 16 bytes, and it operates on 10 rounds, and likewise AES 192 operates on 24 bytes, okay, and so on, and it has got number of rounds is 12, and likewise AES 256 operates on 256 bytes or 256 bits of key and has got 14 rounds for its encryption. Each round has got different steps, as I said, for doing the XORing with the key, and that is typically done by round key addition. It also does several like functions for confusion, which is often done by a process which is called as byte substitution, which we will see in the next classes. So it also does interesting diffusion. It has an interesting diffusion layer, which is done by shift row and mixed columns. And the final round does not have mixed columns because it doesn't add to any conventional security. So therefore, right, what is AES? We will be like looking into this in the next class, and there are I would like to mention here that in the original proposal for AES there were different algorithms which were like proposed, but Reindl, or as was the name of the original algorithm, that won over several other algorithms because of not only security but also because of implementational advantages. Okay. So this is this particular cartoon or stick diagram I have taken from this like this URL. So I would like to thank for that, and finally, right, we will try to take a look into how the AES looks like, and that is something that we will be trying to study in more details in the next classes. Okay. So here I would of course, like I have tried to give you an overview behind this cryptographic algorithms, but we will be studying about like AES in more details in the next classes. Okay. So this is my reference for the book, and so what we basically studied is we tried to understand that cryptographic implementation should be lightweight because we need to ensure that our designs have less overweight. We studied about different types of ciphers or broad types of ciphers. We studied about block cipher constructions constitutes of both nonlinear and linear components, that means which produces the confusion and the diffusion respectively. We studied about the fact that encryption algorithms are published, the secret is often in the key, and we discussed about an idea of differential attacks. We also discussed that AES is composed of different sub operations, add round key and byte substitution, which we will take up in more details in the next class. Okay, so add round key, byte substitution, shift rows and mix columns. So these are different operations which we will try to study in the next class. Okay, so with this I would like to say thank you.